So we have an example of a graph, and it says the graph in the accompanying figure shows the average annual percentage change, y equals f of t, in the US gross national product, GNP, for the years 2005 through 2011. Graph dy dt where it's defined. And so we're given our function f of t, and we want to graph the derivative function. This one is not as bad because look at this. It looks like that each piece of this graph is a line. We can kind of think of this as a piecewise function. And so let's look at this first piece. Notice that it's decreasing here. And we could probably pretty much figure out what that slope is, right? This is looking like this y value here is 6.5. Let's say that we're coming down to 5.5. So I'm decreasing 1 as I go over 1 year. So it looks like from 2005 to 2006, my derivative function f prime of t is equal to, it's the slope again, so we're going down 1, so -1 all over running over 1. So this is equal to -1. So let's just graph that. That's just a constant. So it's saying my derivative is a constant. So when I graph a constant, that's just a horizontal line. And so we have, note down here. So in 2005 to 2006, we have a function that looks like -1. Oops. We do need to go below the x-axis. And it's a horizontal line. So starting at 2005, that's solid. And we're going to 2006. So notice that, remember, we don't have a derivative. Our function is not differentiable at sharp corners. So notice that there's this sharp corner now as we go from here to here. I also notice that it's increasing from there to there. So let's look at what's happening on this stretch of the graph. And so that's from the years 2006 to 2007. So those are the x values, that's interval notation. I can see that f prime of t, the derivative function. So let's see what we're doing. It looks like we are going from this 5.5 to maybe 5.75. So f prime of t, we're raising how much? Well, from 0.5 to 0.75, I can look at that change, 0.75 minus 0.5, that's 0.25. And then how many years? I'm going from 2006 to 2001, I'm running over 1 in the t direction. And so my derivative function here is again equal to a constant. And so this is going to be a horizontal line, y equals 0.25. From 2006 to 2007. And so if this was 1, 0.25, so about right here. And open circle, because it's not differentiable there, to here. And an open circle, because it's not differentiable at 2007, because we have another sharp corner there. So you would just go through each piece. And now 2008, so 2007 to 2008, we want to find what is the slope there. Again, it's a line, it's decreasing. So let's say that was, okay, let's write it as points. So 2007 is the t value. My y value, we had said that that was 5.75. So that's the point. And we have a point at 2008. Our y value there looks like a 0. I'm sorry, not 0, looks like 1. So let's look at the rate of change at that piece. So we have 1 minus 5.75 all over 2008 minus 2007. So 1 minus 5.75. Well, 5.75 minus 1 is 4.75, but the larger number was negative. So it's negative 4.75 all over 1. And so we're going to be below the x-axis. This piece of the derivative is going to be a horizontal line at negative 4.75. And we're going to have open circles. So that was what? At 2007, 2008, and it's going to be a horizontal line. So I'm going to, I think, stop there, but you can get the idea of what you would have to do to get the rest of the graph of the derivative. That way we can go through and do more problems. Let me see, though, if you guys have any questions, or if you really do want me to go through it more, I can. So it looked like you guys were getting it. This was another problem that I have brought up that I was going to have you go through together, but it's pretty similar to what we were just doing. They wanted us to graph the derivative, so we would go through the same way we were just doing. But it also wants to know on this line segment, on the interval from -4 to 6, where is the derivative function not going to be defined? Give your reasons for the answer. So you should be able to find where the derivative function is not defined by looking at the graph of the original function. And we talked about there's different cases where that can happen. Sharp corners were one of them. If we had a vertical asymptote, that would be another place that the graph doesn't. If we had any jumps in the graph of our original function, it wouldn't be differentiable. Well, that graph doesn't have any jumps. Or if we have any fast oscillation in between, and it's oscillating so fast, it's not going to any one particular value, that would also be a place where it's not differentiable. But we don't have that case either with this graph. So only thing that we really have to worry about are these sharp corners, and those are going to be the places where this is not differentiable. So it's not differentiable, or the derivative is not defined when x is equal to 0. Another sharp corner here. So this is when x is equal to 1. Another sharp corner here. So when x is equal to 4, that's the last sharp corner. It can be differentiable at an endpoint. And so if we're looking at a closed interval, it's going to be differentiable at the endpoint if its left-hand side limit, this case actually is the right-hand side limit, would be what the slope would be. So if we looked here at the limit right here as actually not going to give me what the derivative is, right? But the derivative to the left of -4 or to the right of -4, that derivative, we can find out what that slope is. And that's what the derivative is going to be at -4. If we wanted to do a left-hand side, looking at is it differentiable at this endpoint, we would look at the slope. What is the slope coming in on the left-hand side of this graph? It doesn't exist on the right because the function isn't defined there. So next example, looking at this graph, it looks like we have a piecewise function. We have what looks like a absolute value because there's that sharp corner V, and that looks like we have a parabola which is facing downwards. And it says looking at the graph over this closed interval, at what domain points does the function appear to be? And we want to look at a differentiable. So we want to know, where does this function appear to be differentiable? So it's not differentiable at sharp corners. So I notice that it's differentiable from -2 until an open interval until we hit -1. And then it's also going to be differentiable in this piece from -1, not including, until we get to 0. It's not defined here. So -1 to 0, that would be parentheses because we're not including those values. Then I notice that this is smooth and continuous until I hit this open circle when x is 2. And so it's also differentiable, not including 0, but getting close to the left. So parentheses 0 to 2 parentheses. Union, and then it's also differentiable from 2 until I hit 3. Continuous but not differentiable. So I see only one spot where this is continuous but not differentiable. I have a jump at x equals 0, so it's not continuous there. And I have an open circle and a point below that at x equals 2, so it's not continuous there, but it is continuous at x equals -1. And then neither continuous nor differentiable. Well, I just kind of stated that. It's not continuous nor differentiable at x equals 0 because of that jump, and at x equals 2 because of that jump.